Assalamu alaikum. Welcome to the new lecture. So in this lecture we'll be discussing about the application of the auto transformers. So the single phase and the three phase auto transformers are employed for obtaining variable output voltages at the output. When used as variable ratio auto transformers, these are usually known as by their trade names such as variac, dimerstat or autostat. A variable ratio autotransformer or variac has a toroidal core and toroidal winding. Here we show only the toroidal winding. A sliding contact with the winding is made by carbon brush, that's like this is the carbon brush as shown in the figure. The position of the sliding contact can be varied by the hand wheel which changes the output voltage. So when this position is taken over here, the output voltage will be 0. When it is changed in the clockwise direction, the output voltage will increase and reach to the exactly equal to the input voltage. And here for this point to this point, it is used to increase the output voltage beyond the input voltage. So auto transformers are also used for boosters for raising the voltage in AC feeder. They can be used for the boosters in AC system to increase to compensate for the voltage drop. As furnace transformers for getting a convenient supply to suit the furnace winding from normal 230 volt AC supply, because 230 volt AC supply may not be convenient or the exact voltage that is needed by the furnace. So it can be used to increase the voltage to get the convenient voltage for the furnace. Auto transformer with the number of tappings are used for starting induction motors and synchronous motors. When auto transformers are used for this purpose, these are known as auto starters. In that case, it will be used known as auto starters. Actually, the induction motors and synchronous motors are usually started at lower voltage, so they can be used to these starters can be used to start these induction motors or synchronous motors by first applying the lower voltage and then increase that voltage slowly by changing this contact in the clockwise direction. Now let us discuss about the rating of the auto transformer in terms of the two winding transformer ratio, that is A. We know that the kVA rating of an auto transformer is equal to 1 divided by 1 minus K into the kVA rating of the two winding transformer. And here K is the transformer ratio, and where K is equal to V2 by V1, that is this V2 divided by V1. This is the transformer ratio of the auto transformer, and it is here we assume this to be less than 1. Now for a two winding transformer, this A will be equal to V2 divided by this V1 minus V2. So when you divide it by V2, this will be equal to 1 divided by V1 minus V1 divided by V2 minus 1. So V1 divided by V2 will be equal to 1 by K. So A will be equal to 1 divided by 1 by K minus 1. So you will try to find out the value of this, or you simply add K to the add 1 to this, and to this it will be equal to 1 plus uh, uh, 1 plus 1 by K minus 1 divided by 1 by K minus 1. It will be equal to 1 by K divided by 1 by K minus 1. So you will multiply this and this by K, it will be equal to 1 divided by 1 minus K. So that means this 1 divided by 1 minus K will be equal to this, since we know that this 1 divided by 1 minus K will be equal to kVA rating of the auto transformer divided by kVA rating of the two winding transformer. It will be equal to A plus 1. So in general, if you are given the ratio of the two winding transformer, you can simply add that to 1 and multiply the rating of the two winding transformer. You will get the kVA rating of the auto transformer. We will see this, but in general this is not always the case. This is the case only when when this K is very close to 1, and when we have additive this polarity. In that case we will be using this formula. So in general we can actually include all the possibilities that we have. The kVA rating of an auto transformer will be divided by kVA rating of the two winding transformer will be equal to A, that is the two winding transformer ratio, plus minus 1 when K is close to 1. It will be plus for definitely additive polarity, it will be minus for subtractive polarity. So this formula will be used for when K is close to 1. So same formula can be used, that is kVA rating of the auto transformer divided by kVA rating of the two winding transformer. It will be equal to 1 plus minus 1 divided by A of the two winding transformer, that is the transformer ratio of the two winding transformer. So this is when K is very small, very close, very less than 1. In that case, K may be very close to 0. So again, plus will be for additive polarity, minus will be for subtractive polarity. We will see all these cases in a while. Yes, in this case, we'll try to use all these formula and see whether they are true or not. So let us take an example. We have a two-winding transformer whose voltage ratio is 2500 divided by 250. So that means its own transformer ratio is A, that is equal to 10. Its rating is equal to 25 kVA. Two-winding transformer is to be now used as an auto transformer. So calculating its low voltage full load current, that will be equal to 25 divided by 250. 25,000 divided by 250, it will be equal to 100 amperes. And for high voltage, it will be equal to 25,000 divided by 2500, it will be equal to 10 amperes. So this will be looking like this. This is 2500, let us say, on the primary side. High voltage current will be 10 amperes, low voltage will be 250, and low voltage current will be 100 amperes. So for connecting this as an auto transformer, there are usually four possibilities: two in the additive polarities, two in the subtractive polarities. Let us first discuss about the additive polarity. What we do in this case, we simply uh, take this and connect it over here. That means we're connecting this point to this point, and then we are supplying input to the whole winding and taking output across the 10 volt, this 10 ampere, that is a low voltage winding, this, sorry, high voltage winding. So we're connecting them in series so that dot and dot will be like this, so that this is minus, this is plus, this is minus, this is plus. So total voltage will be additive. So when total voltage of this winding will be additive and we are supplying input to this, so the rated voltage of this whole winding will be equal to summation of 250 plus 2500, it will be 2750. So when we connect them in as the auto transformer, their current rating will of the individual winding will not change. So that means the current rating of this winding will be 100 amperes and the current rating of this winding will again be 10 amperes. Now the currents in the winding, the current direction in the winding are such that in one winding, if the current entered is at dotted terminal, and in another winding current has to leave at the dotted terminal. For example, if I use here the current is entering in the dotted terminal, current will be leaving at this dotted terminal. If other words, if I use that the current will be entering at this dotted terminal, current will leave at this dotted terminal in that case. So here I'm using in this case so that this is the low voltage winding and its current rating will be equal to 100 amperes, and I am assuming that current is entering in this dotted terminal. When the current is entering in this dotted terminal, so that in this dotted terminal current will leave, so current direction will be upwards here, it will be downwards here. So this current will be actually the summation of 2. You can use the KCL, you can calculate the value of current over here, it will be equal to 110 amperes. So this is one configuration. Another configuration is that we are taking this to the output side. That means we are taking output at the whole current, sorry, whole winding, and we're giving input to the high voltage winding. So that is 2500. So in this case, we're assuming that the current is leaving at the low voltage winding, and current, when we assume that current is leaving at low voltage winding, in this case we are assuming that current will be, this will be load side, current will enter to the load side. So it will leave at this point and definitely it has to enter at this point. So here it will enter. So this will decide the current direction, and this is the case, this current will be equal to 110 amperes. So this 100 amperes will be the rated voltage of this winding, that is a low voltage winding. High voltage winding has a rated current of 10 amperes. Now here K is equal to, that is the low voltage side is 2500, that is this one, divided by 2750, that is 25 by 27.5. I have kept it as it is. So you can find out its total kV, it will be equal to 25, that is the kV rating of two winding transformer, divided by 1 minus this kV, that is called 275 kVA. This can also be calculated as A plus 1 into 25, where A is the transformer ratio of the two winding transformer, that is 10. A plus 1 is 11. 11 into 25 is equal to 75. Now this can also be calculated by using the current and voltage relationship. For input, the voltage rated voltage is 2750, the input rated current is 100. So when you multiply it, it will be equal to 2750 into 100 will be equal to, at the output side, the rated current will be 110 ampere and the rated voltage is 2500. So when you multiply this, it comes out to be 275 kVA. So in both the cases, it will be same. You can see here, this is the input side, 2500 into 110. This was actually in earlier case, it was output side. So it will be 275 kVA. So you can see that the enhancement of the kVA. Again, the second thing is the same thing. We have used the input as the total winding, but instead of using the output at 2500, we'll take the output as 250 volt. That is the low voltage winding. This is the low voltage winding 2500. Again, this the additive polarity current direction will be as per we are assuming here the current is entering, here will be current will be leaving. The output current will be again 110 amperes. Now the kVA, let us first calculate this kVA by the current and voltage relationships. The input voltage will be 2750 and input rated current will be only 10 amperes. That means 2750 into 10, that will be equal to 27.5 amperes. So 27.5 kVA will be its kVA rating. It has improved, but it has not improved as has improved in this case. So for this case, that means we are taking this as input and this as output. So this will be 250, 110. This will be similar to that of this. So if we assume this to be the current leaving at this point, the current has to be entered at this point. This is 100 ampere for low voltage winding. For high voltage winding, it will be 10 amperes. This is 2750 for the input, 250 into 110 or 2750 into 10. So it will be equal to again 27.5 kVA. You can also calculate it by using this key value. K is equal to 250 divided by 2750. It will be equal to 25 divided by this. It comes out to be 27.5. One thing I actually forgot to tell you, that the inductive kVA will be given by K into kVA. K is equal to this what is the key is this 27 25 by 27.5 275. This kVA has to be the kVA of the whole auto transformer. It will be equal to 50 kVA. This is the conductive kVA. Inductive will be equal to 1 minus K into kVA. It will be equal to 25 kVA. This can also be calculated. The input power is 275 kVA. The inductive kVA will be equal to this voltage multiplied by this voltage, that is 250 voltage into 100, or this 10 into 2500. Actually this inductive kVA will always be the kVA of the two winding transformer, because this also has a kVA which is actually transferred by the induction of the transformer or transformer action. It will always remain this 25 kVA. So inductive will be 25, conductive will be total power multiplied by, sorry, minus the inductive, that is 275 minus 25 will be equal to 250 kVA. For this case, inductive will again be equal to this 25. You can see 2500 into 10, this is 25 kVA. Here also 250 into 100, it will be equal to 25 kVA. So what will be conductive? Conductive will be total power, that is 27.5 minus 25, it is 2.5. 2.5 kV. Here conduction power has reduced because K here is very less. One more thing that you can check here, you can check here that the value of this kVA will be, since A is very less than 1, it's the additive polarity. So you will use this 1 plus 1 divided by this A is 10 here. So 1 plus 1 divided by that is 1.1 actually, because this is 10, 1 divided by 10 is 0.1. So it will be 1.1 into 25. When you multiply 1.1 into 25, it comes out to be equal to 27.5 again. So this formula is valid for this case. So in subtractive polarity, this will be similar to that of this configuration, only this winding has been reversed. This dot has been put over here. You will see the current direction here will reverse. Rest will be same, and the total voltage that will appear across the input will be equal to 2500 minus this, it will be equal to 2250, and the current that is supplied to the output, rated current, will be only 90 amperes. So in this case the rating will be 2250 into 100, that is 225 kV, or 2500 into 90, that is 225 kV. So inductive power, you can see from here to here, it will be 25 kV. If this multiplies with this, again 25 kV, same as that of the earlier one. So conductive power here will be 200 kV. You can also check kV is equal to A minus 1 into 25, that is A is equal to 10, 10 minus 1 is 9, 9 into 25 is 225 kV. This is the formula here, because this K is here, K is close to 1, so we have to use this formula for subtractive polarity. The last case is this, that subtractive polarity, when we are taking the output. In the earlier case, we are taking the output at the high voltage winding of the two winding transformer. Here we are taking the output at the low voltage transformer, low voltage winding of the transformer. So in this case, this will be again 2250, this will be 10 ampere, this will be 100 ampere. That means the current here now will be inwards, current direction will be changing now. So what will be the rating of the transformer? It will be 2250 into this 10, that is, or 250 into 90, that is 22.5 kV. Inductive power will again be equal to same, that's 100 into 50, 10 into 8, that is 25 kVA. And conductive power will be equal to 25 minus this, it will be negative. In that case, it will be actually supplying power to the source. So these type of transformer, we can say action, or these type of transformer where A is very small is not usually used. The auto transformers where A is very close to unity is particularly used. You can see that, and we'll see in the next problem, that the saving in the case when A is very close to unity is very large. So kVA, we can use this formula as well, is equal to 1 minus 1 by A for subtractive polarity, where A is 1, A is 10, 1 by 10 is 0.1, 1 minus 0.1 is 0.9, 0.9 into 25 is equal to 22.5 kV. So usually in most of the cases it is used as this case additive polarity, and the voltage is taken at the high voltage winding, so that output voltage is taken across the high voltage winding, or input is given to the high voltage winding, so that the K ratio will be equal to close to 1, that is 2 to 2500 divided by this. Or in case of subtractive polarity, even if that is less than this of additive polarity, the kVA, total kVA, but still the kVA is very high as compared to the two winding transformer, so it can be used like this in subtractive polarity, or in additive polarity it can be used like this. Now let us try to do some numerical problems, and it will be very much helpful in understanding this. So a 12,500 by 2,500 transformer is rated at 100 kVA as a two winding transformer. If the windings are connected in series to form an auto transformer, that will be, what will be the possible voltage ratios and output? Also calculate the saving in conductive material. So we need to calculate these things. Possibility, actually there will be four possibilities, but here we'll be only discussing two possibilities. So rated current in the high voltage winding will be equal to this 100 kVA divided by 12500, it will be 8 amperes, and on the low voltage winding this rated current will be 40 amperes. So this is the high voltage winding, this is the low voltage winding. We are connecting them in series. The total voltage will be the summation of these two, and we are using them this is actually subtractive polarity, sorry, not subtractive polarity, but additive polarity. The dot should have been over here, so that's why when dot is over here, in this case current is entering this, and here the current is leaving the dot terminal, so that the current direction will be as per this. So dot here will be at this point. So this will be 1500, this will be 2500, this will be 12,500. So I1 will be 40, I2 will be 8, total current will be, I2 will be equal to 48 amperes. I don't know why it has written as 52.17 amperes. This is 48 amperes, and the total voltage across the load will be equal to 1200 and 12,500 volt. So it is to be noted that if the winding of the two winding transformers are connected in series to form auto transformer, the current in the two windings should not exceed their rated values. Now we have already put the limiting value to the current. To form an auto transformer, two windings may be connected in the following two ways. So first configuration, the winding AC, that is this winding, is for 2500 volt, and the winding BC is for 12,500 volt as shown in the figure. So VAC will be this, VBC will be this, and V1 will be the addition of these two, that will be 15,000 volt, and V2 is equal to VBC will be equal to 12,500 volt. So the voltage ratio will be now 12,500 divided by 15,000. That is given by this 12,000, that is 5 by 6. So I2 will be equal to IAC plus IBC, that is for 40 plus 8. That is what I just told you, that will be equal to 48 ampere, not 52.17. So the kVA rating of this transformer will be now V2 I2 divided by 1000. V2 is 12,500. That is this 12,500 into 48. It will be 600 kVA, or it can be equal to 15,000 into this 40 ampere. It will again be equal to 600 kVA. This can also be calculated as 2 winding transformer kVA divided by 1 minus K. K is this, which is also equal to A plus 1 into the 2 winding transformer ratio. That's 5 plus 1 into 100, 600. 100 divided by this 1 minus 0.833, so also be 600 kVA. So for secondary side, 15,000 into 40 will be equal to 16. What is the saving of the conductor? That is K1. That is K actually, that's 5 by 6. That is 83.3% will be the percentage saving. That is why I told you that this K should be close to 1. As it will be close to 1, the percentage will be saved as a copper. So if this K is less than very, you can say close to 0, there will be less copper will be saved. So this is the total distribution of this figure, current and voltage distribution. Now the second distribution will be the same thing, but the output will be taken across this voltage, that is the 2-5 low voltage winding. So here the winding AC is for 12500 and BC is 2500. So as shown in this figure, therefore VAC will be 12500, VBC is 250. So V1 will be equal to 15,000 as it was in the earlier case, but V2 will be equal to 2500. So here current will be 8 amperes, here current will be again 40 amperes, the dot will be now this. So here it will be 48 amperes. Now what will be the voltage ratio? That will be equal to 2500 divided by 15,000, it will be equal to 1 by 6, that is 0.167. Now the I2 will be equal to 48 amperes. The kVA rating will be equal to V2 into I2, that is 2500 into 48, that is 120 kVA, which is also equal to V1 into I1. Actually it has used here dash to differentiate it with the previous case. So it will be again equal to 120 kVA. This can be also calculated by this 100 divided by 1 minus 1 divided by A. So it will be equal to 120 kVA. We can use this also. Here the saving in the conductor material is only 1 by 6, that is 16.7% only. So here as A is very small, so here also we cannot use this type of configuration. In both the configuration we have used the additive polarity. We can use the subtractive polarity to also discuss, or we can say discuss the saving of the material and also the kVA rating. That is up to you, and I hope that you can do that. And that part is the we can say second assignment to you, a part of the assignment first, second part of the assignment first. As first was the phasor diagram, the second will be you have to do it for the two cases for the subtractive polarity. So the last date for that will be decided in the class. I will let you know the last date for that. It will be probably last date for that case will be on Tuesday. That is the Tuesday that will come after this class. Okay, let us try to do one more numerical problem. A 2220 kVA transformer, actually example 3.7, where we have done the short circuit test and open circuit test. It is connected in such a way so that it acts as an step up auto transformer, in which AB is this AB is 200 volt and BC is 2000 volt. Okay, the 200 volt winding has enough insulation to withstand this to the ground. Okay, calculate the low voltage and high voltage rating of the transformer. Its kVA rating, kVA referred inductively, conductively, its efficiency at the full load, that is 0.8 power factor lag. Now simply V1 will be equal to this 2000, V2 will be equal to 2200. So I2 will be now equal to, that is calculated for this case, that will be equal to that should be the rating of this, that is 200, that is 100 amperes. This should be now 200 amperes. This I1 minus I2 should be the rating of this low voltage winding, sorry, this high voltage winding. It will be equal to 10 amperes, that is 20,000 divided by 2000 will be 10 amperes. So I1 will be the summation of these two, it will be equal to 10 amperes. So here current is leaving, here current is entering in this case. So now the input kVA for this it will be equal to this V1 is how much? 2000, not 2000, yes, 2000 multiplied by I1 is 110, it comes over 220 kV. So in this case V2 is 2200, I2 is 100, it will be again 22,000 or 22 kV. It is seen that 20 kV two winding transformer has a rating of 220 kV as auto transformer, 11 times increase. This can be done by this also, that is 20 into 10 plus 1, that is 220 kV. You can use the auto transformer ratio here also, that is it will be equal to 20 divided by 1 minus k, where k here will be equal to this 2000 divided by 2200, that is 1 by 11. When you do the same thing, it will again be equal to 220 kVA. Now the kVA transform inductively will be equal to V1 into I1 minus I2 divided by 1000, that is this V1 multiplied by this current. V1 is 2000 multiplied this current is only 100, that is 20 kVA. Sorry, this will be 10, this will 20 kV inductive, and it will be exactly same as this one. This will not never change. So transformer at this kV transformer conductivity 220 minus 20, 200 kV. So for the efficiency, we know that from example 3.7, core losses will be 120, copper loss will be equal to 300. So efficiency will be equal to, at this type of the load, that is 220 kV into 0.8 is 176 kilowatt. 176 kilowatt divided by 176 plus 0.12 plus 0.3 comes out to be this value, or you can use this formula to calculate. So the two winding transformer, and the same transformer when connected as a two winding transformer, its efficiency was calculated 97.44%, but when it is connected as high voltage, this auto transformer, it is efficiency has increased to 99.76. So the reason for high efficiency for the auto, it is its higher output for the same excitation voltage and excitation current, that is the same losses. So that is why its efficiency increases. So we can say that this auto transformer has the increased efficiency for the when we use the same auto transformer. Now let us discuss about the parallel operation of the transformers. Until now we are discussing about the auto transformer. Now we'll discuss how the transformers are operated or connected in parallel. When the primaries and the secondaries of the two or more transformers are connected separately to the same incoming and outgoing lines to share the load, the transformers are said to be connected parallel. So let us say we have two transformers. This is the primary of one transformer, this is the primary of second transformer, this is the secondary of the first transformer, this is the secondary of the secondary transformer. You can see that they are connected parallel when they are this part and this part is connected to one line of the input or the supply, another input will be connected by this line. So the another terminal of the transformer, that is the primary, are connected together and connected to the supply. So these two will be connected, or we can say they are connected in parallel. Primary. Second is also connected to the parallel. They are first, this terminal is connected to this terminal. You can see through this line, and this terminal is connected to this line through this line, or this terminal is connected to this terminal through this line. And then output is taken from this point to this point, or this point to this point. Since they are in parallel, it will run in the same thing, or it has shown at this point to this point, it will be again the same. So this is how the transformers can be connected in parallel. The two single phase transformers A and B are placed in parallel as shown in the figure. Here the primary winding of the two transformers are joined to the supply bus bars, these are the bus bars, and the secondary winding are joined to the load bus bars, these are load bus bars, these two. Under this condition, V1 is the primary applied voltage, V2 is the secondary load voltage. V1 is the primary applied voltage, V2 is the secondary. And these voltages are the rated voltage of the transformers. Now there, before going into the actual can say explanation of the parallel operation transform, we need to know why do we do the parallel operation, why do we connect the transformers in parallel. When the load on a transmission line increases beyond the capacity of the installed transformer, to overcome this problem, one way is to replace the existing transformer with a new one having the largest capacity. So this is one way of doing it, replacing it. For example, we have a 250 kVA transformer. Now the load has increased to, let's say, 300. We replace it by a 300 kVA transformer. This is called augmentation of the transformer. And the other way is to place one more transformer in parallel with the existing one to share the load. So the next other way is that to keep the first transformer here, and we bring the another transformer, let us say after 100 kV of or of the same kVA rating, and put it in parallel with the existing transformer to share the load. The cost of replacing the transformer is much more than placing another one in parallel with the existing one. So if we bring the transformer which is having more capacity as compared to existing one, the cost will be more as compared to placing another transformer which is comparably having the same rating. Hence, it is desirable to place another transformer in parallel when the electrical load on the existing transformer increases beyond its rated capacity, because we need not to first replace the transformer with the transformer of higher rating. The cost will be higher. The second one is there will be other charges of replacing the earlier transformer, and the third one is that we need to place this transformer to uh, other place so as it should be utilized, or it should be kept, or we have to manage some space for the we can say replace transformer. So these are the drawbacks of replacing it with a new one. Sometimes the amount of power to be transferred is so high that it's not possible to build a single unit of that capacity. Then we have to place two or more transformers in parallel. This is one more advantage. Hence, parallel operation of transformer is necessary, and the amount of power to be transferred is much more than that which can be handled by a single unit. So in that case also we have to use the parallel operation. At the grid substation, CPA transformers are always necessary to ensure the continuity of the supply in case of breakdown. So sometimes it may be used in the distribution also, but in most of the cases in substations or grid substation we keep one transformer as a CPR. So the size of the CPR transformer depends upon the size of the transformer placed at the grid substation. Definitely the size of the CPR will be same as that of the used this substation. Therefore, it is desirable to place a transformer of smaller capacity in parallel to transform the given load, which is in turn reduce the size of the spare transformer. If we use the spare transformer, uh, and if you use the concept of the parallel transformers of different rating, so keeping the spare will also be of smaller rating. So in that case, this will be the advantage of using the parallel transformer. So I think today it is enough for this class. We'll continue with the parallel operation transformer in the next class. Thank you.